KURINJI Senior Secondary School, CBSE, Namakkal.
Successful result producing school in state every year.
Administered by the Board of Directors with over 35 years of experience in the teaching field.
Special attention on art, craft, music, dance, silambam, yoga, skating and karate.
Focus on Hindi Sabha and Spell Bee Olympiad exams.
Smart class for effective and innovative learning and well-furnished library.
Solitary importance on sports and games in state and national level.
WhatsApp facilities to know activities of students and school inside the campus.
Neet, JEE, IIT coaching experts from Rajasthan and Andhra Pradesh along with our effective teachers.
Admission registration for classes LKG to +2.
KURINJI Educational Institution, Kavetipatti, Namakkal. Admission in progress. CBSE, KG to 12, contact 9025895176. Metric 6 to 12, contact 9344567484. For online admission, log on to www.kurinjischoolnkl.in.
In continuation to the last class, this is third class from the chapter Dear Nature of Light. Okay, right. So in our previous classes, we discussed what is work function, what is photoelectric effect, and then what is threshold frequency and what is threshold wavelength. Okay, right. So I request you, from the starting of this chapter, our concentration is basically on photoelectric effect. Photoelectric effect. Okay, right. When a metallic surface is exposed to the electromagnetic wave, that is what light. Okay, when a metallic surface exposed to an invisible form of energy, that is light. When a metallic surface is exposed to the ultraviolet radiation, that is light, the emission of electrons takes place. The emission of electrons takes place from the metallic surface. From the metallic surface. This is the natural phenomena. This is what we are calling it as photoelectric effect. Here, basically, conversion of energy is taking place. That is what, light is a form of invisible energy. When the energy is going to incident on a metallic surface, metal means it has, that is what, like sodium and like aluminum and like copper, right? And it has its own electronic configuration. That is what you can write it in our periodic table also it is there, right? Okay. And when the electrons gains, metals having their own, that is what valency, right? So the number of free electrons, generally the electrons which are present in the outermost orbit are free when compared to the innermost electrons, right? So in a metal, not only electrons, not only negative charges, positive charges also present, right? So when a light, that is what invisible form of energy incident on a metallic surface, these free electrons gains energy and these free electrons will tries to escape from a metal. But in the same metal, positive charges also present. Positive charges also present, right? When these electrons are trying to escape from the metal, the positive charges pulls back because attractive force is there now, right? So these positive charges pulls back these electrons. Okay, right. So when these electrons overcome that attractive force, and it depends upon the energy of the incident energy of the incident radiation, then these electrons will come out from the metallic surface. That's what we are calling it as emission of electrons from a metallic surface. This is what we are calling it as photoelectric effect. Phenomena wise okay, but when the electrons will come out, to come out the electrons from a metallic surface, What is the minimum energy required for the incident radiation? What is the frequency of the incident radiation? What is the wavelength of the incident radiation? Right? And these factors are very important. Our previous classes concentrate there only. Okay? That's what I want to say before starting of this class. Okay? Right. That's why there itself we discussed what is work function and what is threshold frequency and what is threshold wavelength. Okay? Right. Work function is the minimum energy of incident radiation, minimum energy of incident radiation required to eject the electrons, minimum energy of incident radiation required to eject the electrons from metallic surface, is defined as the work function of that surface, right? As simple as such, work function is the minimum amount of energy, right? So that is what the minimum energy of incident radiation required to eject the electrons from metallic surface, okay, right? And that you can write it as H nu naught, W naught is equal to H nu naught, right? As I told just before 2 minutes, when you are going to study the relation between the frequency of incident light and the emission of electrons, there itself you can talk about the definition, that is what threshold frequency, right? You can say that the minimum frequency of incident radiation, the minimum frequency of incident radiations required to eject the electron from metal surface, the minimum frequency of incident radiations required to eject the electron from metal surface is defined as threshold frequency, okay, right? Next, what is threshold wavelength? Okay, the maximum wavelength of the maximum wavelength of incident radiations required to eject the electrons from a metallic surface is defined as threshold wavelength. Okay, right. As simple as such, in a simple manner, you just remember work function is the minimum energy of incident radiation for the emission of electrons from a metallic surface. Threshold frequency is the minimum frequency of incident radiations to eject the electron from a metallic surface. Threshold wavelength is the maximum wavelength of incident radiations required to eject the electrons from a metallic surface, right? So that's these three things I request you to remember in your mind, right? Because it is very important for us at every step of this discussion, right? Next, see here, Einstein's photoelectric equation, right? See this. According to Einstein, photoelectric effect is the result of 1-to-1. According to Einstein, photoelectric effect is the result of 1-to-1 inelastic collision. 1-to-1 inelastic collision between photon and electron. In which photon is completely absorbed. Okay, so I will repeat once again. Here, according to Einstein, photoelectric effect is the result of 1-to-1 inelastic collision between photon and electron, in which photon is completely absorbed, right? This is what coming, that is what so the radiation, that is what incoming radiation, and here we have electrons, that is what like free electrons, and when the incident radiation is coming, that is going to absorb by the electrons, in a metal, right? So when these electrons absorb the energy from the incident radiation, these electrons will get the movement, these electrons will go into the motion, then they also will go out of the metal. That is what we are observing in case of photoelectric effect. Okay. So when the electron comes out from a metal, when there is a velocity and mass of electron also we know, so you can say that the electron is having certain amount of kinetic energy. Certain amount of kinetic energy. Okay. Right. So here regarding this, you can say that the energy of the incident radiation, is equal to the work function. That is what the energy required for the electron to come out from the metal, and the kinetic energy of the electron, right, with which the electron is present after the metal surface. That is what after a metallic surface. Okay, you can see this equation. That is what E is equal to W naught plus K maximum. E is equal to W naught plus K maximum. That is what Einstein's photoelectric equation. E is equal to W naught plus K maximum. Here the important point we have to understand is, whatever the energy of incident radiation, that is equal to the sum of these two. This is the amount of energy required for the electron to come out from the metallic surface, and this is the energy possessed by the electron after came out from the metallic surface. So that is what K maximum, right? For example, it is 10 joules. It is, for example, not exact. It is 10 joules, it is 2 joules. Then what about this? It is 8 joules, no. So the kinetic energy of the electron is 8 joules, like that, right? It is like equation which gives the relation among three things. That is what energy of the incident radiation, and energy required for the electron to come out from a metal, and the kinetic energy of the electron. Okay, right? Where it is the general formula, K is equal to half mv square. We don't know. So K maximum is equal to 1 by 2 into m into V maximum square. That is what maximum kinetic energy of emitted electrons. Maximum kinetic energy of emitted electrons. Okay, and you can see here that is what radiation which is coming and the electron which is going, right? Energy is generally h nu. Okay, energy is generally h nu, right? We need not to bother about that especially. Okay, so that's what I want to say. Okay, energy is generally E is equal to, you can see this picture, it is what the kinetic energy is 0 here. That is what so whatever the energy incident on a metallic surface, if the energy is just enough for the electron just to come out from a metal, in that case you can say that the kinetic energy is 0. Just the electron came out and it is not in motion, right? So when it is not in motion, very well the velocity is 0, no, right? So when the velocity is 0, the kinetic energy is 0. So momentarily at rest. But here if you observe carefully, E is equal to h nu, and the energy of the incident radiation is sufficient for the electron to come out, and also certain amount of energy is, that is what available, right? So there itself we can say that the electron is moving with some speed. So there itself we can say that it is moving with some kinetic energy. That is what kinetic energy maximum. Okay, right? So you can write this expression, that is K maximum is equal to half m into V maximum square. K maximum is equal to half m into V maximum square. Next, effect of intensity and frequency of light. Effect of intensity and frequency of light. First we are going to study the effect of intensity. Effect of intensity, right? So as the intensity of light is increased, what happens? That we are going to discuss. See here. See this, ma. If the intensity of light is increased while its frequency is kept the same. So we are studying the relation between intensity of light and the current, that is what photocurrent. That's why we kept the frequency is constant. So if the intensity of light is increased, the current levels of at a higher value, the current levels of at a higher value, showing that more electrons are being emitted per unit time. More electrons are being emitted per unit time. So what he is saying, if the intensity of light is increased, the current levels of at a higher value, if the intensity of light is increased, the current levels of at a higher value, showing that more electrons are being emitted per unit time. Showing that more electrons, suppose for example there are 10 electrons, intensity of light is increasing, then what will happen? If all the electrons came, or more number of electrons came, means what can we say? More electrons are being emitted per unit time. But the stopping potential V0 doesn't change. The stopping potential V0 doesn't change. Okay, right. So that's what he is saying. So at this moment, so the stopping potential V0 doesn't change. What is meant by stopping potential? We have to recall. So what is meant by stopping potential, right? So stopping potential is actually the potential of, that is what collector plate, the potential of a collector plate at which no electrons can reach, collector plate. That is what we are calling it as stopping potential, right? That is, suppose if you are assuming one is P, another one is Q, in case of that vacuum tube or discharge tube, right? And generally Q is at, suppose for example, that you can change it as either plus or minus for P and Q, right? Generally P is, that is what emitter plate, and Q is what collector plate. Okay, right. At a particular negative potential of plate Q, no electron reaches the plate Q and the current will become 0. This negative potential is called as stopping potential and denoted by V0. So which is what we discussed in the first class of dual nature of light. Okay, right. And next is this relation is very important. If possible you underline, okay, and you also read many times just to memorize. And see here this relation, intensity is directly proportional to number of incident photons. Intensity is directly proportional to number of incident photons. E is directly proportional to number of emitted photoelectrons per time. Number of emitted photoelectrons per time. E is directly proportional to photocurrent. E is directly proportional to 1 by distance square. 1 by distance square, right? So try to understand this relation. At the same time, we have to keep in mind what is what, right? See here, intensity of incident radiation. E is directly proportional to the number of incident photons. Number of incident photons. E is directly proportional to the number of emitted photoelectrons. Number of emitted photoelectrons per time. Number of emitted photoelectrons per time. Okay. E is directly proportional to the photocurrent. That is what the ultimate thing, no? Right? Photocurrent. E is directly proportional to the 1 by distance square. 1 by distance square. Okay, right. And you can see this graph also. That is what intensity and it is what the current. Both are directly proportional. Because of this direct proportional symbol, that is what the relation, we are getting like this graph. That is what a straight line passing through the horizon. Right? Based on this relation, we are getting this graph. And in mathematics subject also, you may got it how to draw a graph and by studying the curve, how can we find the relation between two physical quantities, right? So graph is a pictorial representation of two physical variables. Graph is a pictorial representation of two physical variables. Okay, right. And you see here another graph. That is what here he mentioned frequency is constant. That is what I already told you the starting of this. That is, while frequency is kept the same, we are studying the relation between intensity and photocurrents. Okay, right. So this is what here it is potential, and this is also, that is what, negative potential. There is no change in the, there is no change in the stopping potential. That is what the stopping potential V naught doesn't change. See here, that's why it is the I curve and it is 2I. So intensity is doubled here, but stopping potential is same. No, stopping potential no change. That's what he is saying through this graph. Okay, right. And now we are going to see effect of frequency. Effect of frequency. Okay, right. Effect of frequency. See here. So just now we completed to study effect of intensity. Now we are going to see effect of frequency. Okay, but here we keep intensity as constant. Our interest, our considering thing is not intensity. We consider frequency, right? So the variation of frequency is our discussion. So if frequency of incident light increase, stopping potential increases. I will repeat once again. If frequency of incident light increase, stopping potential increases, but there is no change in photoelectric current. There is no change in the photoelectric current. If frequency of incident light increase, right, frequency of incident light increase, stopping potential increases, but there is no change. There is no change in photoelectric current. In photoelectric current. Okay, right. You can see this one, that is what it is. I is constant, as I told you already. It is what potential, and it is the frequency, not the potential. It is nu, right? Like this, the frequency 1, and it is like frequency 2, and this one is greater than this one. That is what nu 2 is greater than nu 1. Okay, and that is what two different potentials. And I already told you here itself, that is what if frequency changes, stopping potential changes, right? But intensity is constant and no effect, nothing to photoelectric current. Okay, right. And whatever the discussion we had till now, we had some important formula. That is what you can see here, important formula for photoelectric effect. Okay, see this. H nu is equal to H nu naught plus K maximum. It is what the energy of the incident radiation, and it is what the energy of, that is what work function, and it is the maximum kinetic energy. And the maximum kinetic energy can write it as E into V naught. E into V naught. V naught is the stopping potential, right? E into V naught you can write. So the same thing we are writing here. And if it is E V naught, if you send this one to that side, H into nu minus nu naught. E V naught is equal to H into nu minus nu naught. That implies K maximum is equal to half M into V maximum square. No, so that is H into nu minus nu naught. And you take this V maximum and you write as a subject, then it will be, that is what 2H into nu minus nu naught by M square root. That is what V maximum is equal to, right? Next, fourth one. So the same thing he is repeating, that is what K maximum is equal to half M into V maximum square, that is equal to E into V naught. That E into V naught you can write like this, that is what C is equal to nu lambda, right? Like V is equal to n lambda, C is equal to nu lambda, right? So when you in place of C, in place of nu you can write C by lambda. Here you can write C by lambda naught. So that you can write it as HC into 1 by lambda minus 1 by lambda naught. The same thing you can also write HC into lambda naught minus lambda by lambda naught. Is a mathematical thing. Is a mathematical thing, right? And from this again he is writing, that is what V maximum is equal to square root of 2HC into lambda naught minus lambda by lambda, and it is the mass, right? And next V naught is equal to H by E into nu minus nu naught, that is what V naught, because it is E V naught, no, it is E V naught, it is when E V naught is equal to h into nu minus nu naught, V naught is equal to h by E into nu minus nu naught, that is equal to hc by E, hc by E into 1 by lambda minus 1 by lambda naught, 1 by lambda minus 1 by lambda naught. Okay, that's what I want to say. These are the important formulas to keep in mind, which are very important for us to solve the problems related to NEET and mains. Next thing, matter waves, right? So what are the matter waves, and otherwise you can also call them as de Broglie waves. Okay, see here, according to de Broglie, a moving material particle, according to de Broglie, a moving material particle sometimes acts as a wave and sometimes acts as a particle, right? So that is what he is saying. According to de Broglie, a moving material particle sometimes acts as a wave and sometimes as a particle, is a statement, natural thing, according to de Broglie. The wave associated with moving particle is called matter wave or de Broglie wave, and it propagates in the form of wave pockets with group velocity. It propagates in the form of, right, wave pockets with group velocity, right? So what I am saying is, the wave associated with moving particle, the wave associated with moving particle is called, the wave associated with moving particle is called matter wave or de Broglie wave, right, or de Broglie wave, and it propagates in the form of wave pockets with group velocity, in the form of wave pockets with group velocity. Okay, right. Next, it is what next thing, particle nature of light. Particle nature of light means the main thing is photon, right? So what is photon means? According to Einstein's quantum theory of light, according to Einstein's quantum theory of light, okay, according to Einstein's quantum theory, right, quantum theory of light, okay, light propagates in the form of bundles. So that bundle is called as pocket or quanta. That bundle is nothing but pocket or quanta. So that is what I am saying. When the light propagates in the form of bundles, that is what pockets or quanta of energy, bundles of energy, each bundle is called a photon, each bundle is called a photon and possessing energy, okay, right. So in this class we focused on Einstein's photoelectric equation, and we studied the effect of intensity and frequency of light, and we discussed some of the important formulas. At last we discussed what are matter waves, and that is what matter waves or de Broglie waves, and then what is the particle nature of light and what is photon. Okay, right. So we will continue in the next class. Thank you.